folks, and the topic of today's video is going to be formal charge. Now, as I mentioned in class, sometimes we're in a situation where we have non-equivalent resonance structures for covalent compounds. And I mentioned to you that we might be in a situation where we could take a look at those non-equivalent structures and then choose one that we think might be preferable over the other ones. Okay, so the whole purpose behind formal charge is we want to use formal charge to identify the most favorable, and that means to us, lowest potential energy resonance structure. Okay, so we're going to come up with the most stable, most preferential resonance structure in that sense. So let's first, before we apply it, define what formal charge is and how we calculate it. So Fc here stands for formal charge. And what it's equal to for any given atom in a structure is the group number of that atom, in other words, the number of valence electrons it normally has, minus the number of electrons actually associated with that atom in the resonance structure. Okay, so the other assumption we make here is that we're going to assume that we have equal sharing of electron pairs in a bond. Now, we're later on going to find out that that may not actually be the case. So let's just look at a simple Lewis structure first, one that we've already done in class, and let's see how we can assign formal charges based upon the Lewis structure. All right, so let's look at CH4, that's methane. And you'll remember from class that I can come up with a simple Lewis structure for CH4 that looks like this. If you're not sure, make sure you go back and reproduce it. So carbon's our central atom. I'm going to surround it with my 4 hydrogens, and I'm going to use an electron pair to form a bond between the carbon and each one of those hydrogens. All right, so what I want to be able to do is show that I've got 4 equivalent bonds here, which means now that I can calculate a formal charge for each equivalent hydrogen, or I can also get a formal charge for the central atom, which is the carbon. So we'll use our formal charge equation to show how we can do that. All right, so let's look at the hydrogen first. All right, so the formal charge is equal to the group number of the hydrogen. Okay, that's also equivalent to the number of valence electrons hydrogen normally has. Now, hydrogen is in group 1A, so it has 1 valence electron. So that's where this particular number comes from, that single electron that I have there. Now, how about the other one? Well, the other one is going to correspond to the number of electrons actually associated with that atom. Now, keep in mind here that we have to assume that the covalent bonded electrons are equally shared between the carbon and the hydrogen. So my little squiggle here represents breaking that bond in half. Now, if I broke that bond in half, one of the electrons is going to go to carbon, and the other electron will go to hydrogen. So a single bond like this will give 1 electron to each atom. Okay? So if that's the case, one of the electrons that goes with hydrogen corresponds to the electron here. Carbon would get the other one. So 1 electron minus 1 electron gives a formal charge of 0. 1 minus 1 is 0. Now let's do the same thing for the central carbon atom here. Now carbon is in group 4A. So you should be able to verify that carbon comes in with 4 valence electrons. Now, that's where this number comes from. Now the other thing that I need to do is to take a look at each one of the bonds to carbon here. So what I'm going to do is I'm going to break each bond, and I'm going to give 1 electron to hydrogen and 1 electron to carbon. All right, so if I do that, I have 1, 2, 3, 4 electrons now that belong to that carbon atom. So that's where this 4 comes from here. So 4 minus 4 electrons gives me 0. So in both cases, hydrogen and carbon, what I've got here is a formal charge of 0 on each atom. Okay, so that's how we calculate formal charge. And we can do that for any element or any atom in a Lewis structure. So now let's go back to our goal here. So our goal, in order to find the best possible Lewis structure in terms of a resonance structure here, is to try to minimize formal charge across the whole molecule. Okay? So let's look at carbon dioxide here as an example. We saw in class that essentially we could come up with 3 resonance structures for carbon dioxide. Here's one, and then we have the 2 equivalent resonance structures here. So energetically, these 2 should be the same, but energetically they may be different from this one because of the distribution of the electrons. Okay? So what I want to be able to do is to calculate a formal charge for each atom in each resonance structure, and then kind of collectively look at the formal charges and see whether or not I can minimize them. All right, so let's look at my one with the two double bonds here first. So what I want to do, again, is I want to think about sort of cleaving these double bonds equally here. Okay, so if I do that, I can calculate how many electrons go to the oxygen and how many electrons will go to the carbon in each case. So let's calculate a formal charge for this oxygen right here. Okay, so for a more formal charge has to equal to the number of electrons an oxygen normally would have, which corresponds to its group number. That's group 6A. So a normal oxygen is going to have 6 electrons associated with it. Okay, now I'm going to subtract from that the number of electrons that that particular oxygen can lay claim to. Okay, so here I have a non-bonding pair that counts for 2 electrons. 1, 2. Here's another non-bonding pair that counts for 2 more electrons. That's a total of 4. And then I have the shared ones here, the cleaved bond, that gives me 5 and 6. Okay? So what I have here is this oxygen laying claim now to 6 electrons, giving me a formal charge of 0 on that oxygen. Now, this oxygen is absolutely equivalent on the other side, so we don't have to do that calculation. But the formal charge for that oxygen also is going to equal 0. It's exactly the same calculation. You can verify it. Now, let's do the formal charge on the carbon. All right, so carbon is in group 4A, so it's coming in with 4 electrons. All right, now let's see how many electrons the carbon can lay claim to. So again, I've cleaved 2 double bonds, so that's going to give me 1, 2, 3, 4 electrons. Okay? So I have here again 4 electrons minus 4 electrons, that's a formal charge of 0. So this is looking pretty good because I've minimized formal charge here across the whole molecule. I got formal charge of 0 on this oxygen, formal charge of 0 here, and a formal charge of 0 on the carbon. 0 all around is the best we're going to possibly do. Okay, so we know that's going to be a good structure. So let's do the same kind of calculation on my other resonance structure that I have. So again, let's think about cleaving these bonds so that each species gets half the electrons. So let's calculate a formal charge over here on this oxygen. Okay, so my formal charge is going to equal to the 6 electrons a normal oxygen would bring in, minus the number of electrons this oxygen lays claim to. Let's count them up. 1, 2, 3, 4, 5, 6, oh, and 7 because of the cleaved bond here. So 6 minus 7 gives me a negative 1. So I'm going to get a negative 1 formal charge on that oxygen on the left. Let's get our carbon. So my formal charge in the carbon is going to be 4 electrons that each carbon should have coming in, group 4A. Now, let's go ahead and count the electrons the carbon can lay claim to. 1, 2, 3, 4. So 4 minus 4 is going to give me a formal charge of 0. Now, let's get the formal charge on that other oxygen. Now, notice this oxygen is different from the oxygen on the left because it's got a triple bond to it. Okay, so again, oxygen's coming in with 6 electrons. All right. Now let's see how many electrons this particular oxygen can lay claim to. 1 non-bonding pair, so that's 2, 3, 4, 5 through the cleaved bond. So 6 minus 5 electrons is going to equal to a positive 1 formal charge. Okay? So in this case, we're not doing as good a job of minimizing the formal charge here. Okay, I've got a 0, I've got a minus 1, and I got a positive 1. Now, it's not as simple as just adding them all up, because if you add a 0 minus 1 and a positive 1, you null out to 0. But the deal here is we have to look at these formal charges across the whole molecule. 0 is good, but a minus 1 is not so good. And a positive 1 is also not so good, because we're not minimizing that formal charge to a 0. So what that means here is that if you were to choose one of these resonance structures as the better structure, it's going to be the one on top, because I was able to minimize all the formal charges across the molecule to 0. So the one on the bottom now would be the less favorable Lewis structure. It's an acceptable Lewis structure, but it's the less favorable Lewis structure from an energetics point of view. All right, folks, we'll come back next time and we'll practice with this a little bit more. So I'll see you next time.